Hello, everyone. I hope everyone can hear me. My name is Negin Sobani, and welcome to Dask tutorial. We are here today to talk about Dask overview and also Dask on HPC. My colleague Brian and I will talk about these. And just a reminder before the beginning of the tutorial, I just want to remind everyone of the code of conduct. And also this meeting is being recorded. Yeah, that's it. And with that being said, I'll start. So the materials for this tutorial will be, or is actually, in GitHub repository. You can find it under NCAR Dask-tutorial. And also it's all rendered as a Jupyter book. So you should be able to follow through them using the Jupyter book. It might be easy to read through them. It's basically a HTML rendered. Today we're going to talk about, it has two sections. First, it would be like a beginner section, and then it would be an intermediate section. The intermediate part will talk about the HPC aspect and best practices. And the introductory part, the beginner part, will talk about the overview of Dask and getting started with different Dask collections and different Dask components. So here you can see the course outline. For following through this notebook, you can do so using NCAR Jupyter Hub. Most of this tutorial, we are actually designed it so that it would be followed through NCAR Jupyter Hub, but and at your own time. But if you want, you can also like play with the first few notebooks on your local machine as well. Yeah, that being said, I'll start with the first notebook. So basically, first I'm going to talk about Dask overview and different Dask components and why one might be interested in using Dask. So overall, Python, it seems like it's getting more popular every day, and especially in geoscience community for data analysis. Basically, a lot of people are using Python, and it has some nice data structures that enable some fantastic work, a lot of data analysis, data science workflows, things such as libraries such as Numpy arrays, and data structures such as Numpy arrays and pandas data frames, or XArray dataset. But a big limitation here, and that's what we are here to talk about, is the memory. These data structures are fantastic, but what if the data set is too big to fit into memory? And that's basically when Dask come to rescue. So Dask basically is a flexible open source Python library that enable us to do parallel and distributed computing. And Dask basically scale Python packages such as Numpy or pandas from one machine, even a laptop, to 1,000 core machines such as HPC machines, HPC clusters, or even on a cloud. And that actually give our users a lot of capabilities, because they can test their workflow on their local machine, and then they can scale it out to a cluster. So that's fantastic. It seems like everyone's using Dask these days, and there are some good reasons for that. Dask has a lot of benefits. So first and foremost, Dask has a very familiar interface. And the interface that it has basically mimics Numpy.
There's somebody who asked.
Yep, yeah.
Oh, sorry.
Thank you so much.
Sorry.
Oh, no worries. Yeah, then notebooks are basically, yeah, you can find them through the link that Brian sent. So Dask has a very familiar interface. It has an interface or API that mimics a good portion of Numpy and Pandas API. And this means that we don't have to rewrite all our codes. And that's actually good, because I have done rewriting my codes from NCL to Python, and I know it's very difficult to rewrite your codes in another language. Another good thing about Dask is that it's very scalable, and we talked about that, and that's why it's getting used more often. Dask also is very flexible. It provides a lot of different tools. For example, you can basically, Dask has tools that integrate with a lot of HPC resource manager, HPC job schedulers such as PBS or Slurm, and also on cloud using Kubernetes. It also has a lot of built-in diagnostic tools. It has a live dashboard that give responsive feedback on how your computations are progressing, and this would be helpful, especially for identifying potential bottlenecks or potential issues and debugging your code. With all that being said, and Dask is fantastic, the first rule of Dask is avoid using Dask if you can. And that's not what I say. I got this screenshot from Dask Twitter that they say that avoid using Dask first, see if you can do your work without using Dask. And there's a good reason behind that. Although Dask is very powerful, it's not always the best solution for all of the problems. And it introduces a lot of, because it would be like basically using it overall, like parallel computing in the distributed, like the distributed setting would add another layer of complexity and another layer of overhead. And overall, it will add to the complexity of your problem. And things to keep in mind is that how much time you'll gain by using Dask and how much time you have to spend on basically porting everything, basically using Dask and like implementing Dask in your notebooks and your scripts. Another thing to consider, for example, is that how many times are you going to use one, your code? If you're going to use it only once, does it worth like spending a lot of time debugging and optimizing your workflow for Dask? And overall, like think about if you can find bottlenecks in your code and try to optimize those bottlenecks. It would be better with or without Dask. These basically tips would be very helpful. Try profiling your code, try to find the bottlenecks and optimize those bottlenecks. If you can read in a subset of your data, that would be a lot better than reading in huge data sets and things like that. So these are some general guidelines of when to use Dask. So Dask is fantastic when you have large data set that doesn't fit into memory and when you want to do parallel computations such as big data analysis. But if you have a smaller data set, as we said earlier, it wouldn't be very beneficial. And if you don't want to spend time debugging and troubleshooting or optimizing your workflow, it probably wouldn't be the best option. So let's talk about the components of Dask. So under the hood, Dask basically has two components. First, Dask Collections or Dask APIs. These are basically the core libraries that Dask has. And second is Dask Dynamic Scheduling or schedulers. So the Dask Collections or Dask APIs basically are the user interfaces that enable us to do the parallel computing. And we can think of them as two levels of basically collections that we have, high-level collections and low-level collections. So the high-level collections are already out of the box and you can use them basically very easily. And you can think of them as a parallelized version of Numpy or parallelized version of Pandas. And there are different ones. This table kind of summarized them very well. They are really good to use, and that should be your first option actually when coming to Dask, trying to use one of these. And they mimic.
Sounds like Miss George can't see your screen. Is that, yeah, can we get a status check from other folks who are viewing remotely?
I can see.
Okay.
Okay.
Awesome. Okay, thanks. Thanks.
Thank
all. Sorry, George. We'll...
This is what I see from.
Did you connect using the companion mode maybe? No?
I'm in companion mode and it's working fine.
Okay, I'm not sure then.
I don't need to see your screen, but that's it.
Heather's suggesting that if you're running into that, maybe try leaving the meeting and re-entering.
So yeah, no worries. So high-level collections basically mimic Numpy and Pandas interface, and they can be used as a drop-in replacement for them. And we have three of there are basically three popular ones: Dask DataFrame, Dask Arrays, and Dask Bags, which is basically a substitute for lists or unstructured data set. But we're going to talk about mostly about Dask Arrays and Dask DataFrames. And the low-level collections are basically a bunch of APIs. Basically, you can think of them that enable users to do a lot of customized things and customized workflows. It gives the user a lot of finer controls over what they're parallelizing, but they are a little bit more complex to kind of implement. But they're very powerful tools, and we have two of them. One is called the Dask Delayed, and the other one is Dask Future. So Dask Delayed is basically parallelize any function that you want. You will add just a decorator on top of it and delayed, and it will parallelize it. And Dask Future is basically enable you to do asynchronous parallelization. We are not going to talk about those two. I was just putting them there so you get familiar with them. And kind of this figure summarize it. So Dask high-level collections are easy to use and they're ready to use right out of the box. But with low-level collections, you can do a lot more customized workflows. The second component of Dask is Dask task scheduling or Dask schedulers. And you can think of Dask schedulers as our task orchestrators. So when we are submitting a computation, when we are submitting our computation, what happens is that the work will be split into different sections and they would be sent to different workers. For this, we need a scheduler, and this is different from HPC scheduler, although they can interface with each other, they can talk to each other. So what they do basically is that they coordinate the workers and they send the tasks to the workers and they kind of organize everything. So to think of a Dask cluster, so these are the components of a Dask cluster. So we talked about Dask scheduler, which basically send the tasks and coordinate between the workers. And the Dask workers do their computations, they compute the tasks and send it back to the scheduler. And another component is the client, which is a high-level interface. And you can think of it as an interway to the scheduler, the way to kind of talk with the scheduler, the way to interact with the scheduler. And again, we will go through all these components in more detail. This was just an overview of what we are going to discuss in this tutorial. So with that being said, I'm going to go to the next notebook, which will talk about Dask arrays. But I just want to see if anyone has any questions. If not, I can move quickly to Dask arrays. Okay, doesn't seem like it. So I'll talk about Dask arrays. So Dask array is basically, you can think of them as parallelized NumPy arrays. They're you can think of them as a bunch of NumPy arrays set together. And what they do basically is that because the computation is split between among them in smaller chunks, basically in smaller subarrays, that enable basically the parallel computation, and that enables the data to fit into memory because it's now smaller, it's smaller chunks. And that's how Dask basically reduced the memory, Dask arrays reduce the memory footprints. One concept about Dask is the lazy evaluation, and the lazy evaluation, as opposed to eager evaluation, means that unlike NumPy arrays that we are familiar with, the operations that we do on Dask arrays are not calculated, not computed until we explicitly ask it to. So that's what we mean when we say Dask arrays are lazy. This means your objects are not evaluated until you explicitly ask it to evaluate them. And you might think that how that can be helpful that can be helpful so that you don't have large pieces of memory around on basically large pieces of data on your memory. So it kind of optimize your resource management. It only use whatever it needs. And we'll talk about, let's explore the Dask arrays and see how they look like. So for the tutorial, we have to start with a client. And here, just know, we'll talk about clients later. Just know that we start a client so that we can have different workers and we can basically use Dask arrays in an efficient way. But we'll talk about Dask clients later in more depth. So one concept about Dask is the blocked algorithm or blockwise algorithm. And that means that the blocked algorithm overall means that the computations are basically divided into smaller pieces, and then the workers do the workers basically do that computation on that smaller piece of data, on that a small subset of data. And that subset of data actually is called chunk, and that's another concept with Dask arrays. And to get familiar, I know like this might not make sense. So I put together an example that kind of explained this better. So here we have a very simple NumPy array going, it's a 4x4 NumPy array starting from 1 to 16. And first we have this NumPy array, and then we convert it to a Dask array. And don't worry about the syntax. Just know that we are basically converted to a Dask array with 4 chunks. So basically 4 squares, you can think of them. Now we want to calculate the sum of this array. It would be basically a similar syntax. So in NumPy array, we use the dot sum, and in Dask, we use the dot sum. So you might think, how is it different? So the difference is nicely shown in this image. Basically, when we want to take the sum on this Dask array, Dask first calculates the sum on each of these chunks. So each of these chunks would be like, for example, calculated first. And then it will do this. It will basically sum of the chunks together to get to the final value. And that's how Dask is basically more optimized. So if you have like 4 workers doing this, it would be much more faster. So now that we talked about block algorithm and we have this image, maybe now it's a good time to talk about task graphs. And bear with me with all the terminology. I just want to get everyone familiar with the terminology. So think of that task graphs as a blueprint. So basically, Dask arrays are empty, and they are just a symbolic representation of the computations that are needed to be done to get to the value that we want. So the task graphs are the blueprint or roadmap that basically says Dask, what are the computation, what are the steps that needs to be done. And the task graph basically has first the relationship between the tasks and the order in which they have to be executed. And basically it shows like all the dependencies. And you can nicely visualize your basically task graph using Dask.visualize method. And that basically gives you how it will look like. So this is basically similar to that figure that we saw above. Basically, it shows that it's doing the sums first on each of these chunks, and then it aggregates all these sums together to get to one number. And overall, it's always good practice to take a look at the task graph to find if there are any potential bottlenecks or if there are any places that parallelism is not possible. And this is called a low-level task graph. We can sometimes, so this was a very easy example. Sometimes with bigger arrays, this task graphs get actually very big and overwhelming very quickly. So you can do a more simplified version of, or more high-level version of the task graph. So this one is an example of a high-level task graph that shows the steps basically here. So now let's start with a real life example. I'm not sure if I actually run, did I run them? Yeah. Okay.
So Megan, I think Jesse's question probably is a good one here. So he asks, does the scheduler do the aggregation or is it just one of the workers?
Correct me if I'm wrong. I think it's just one of the workers that do the aggregation.
Yeah, so the scheduler is never doing any of the actual computational work. It's coordinating it. And then, if you have chunks of, if you have operations, they're going to occur on all the workers. And then when it aggregates down, if that's a step that's only going to require, say, one worker, it's still going to run on one of those workers and not on the scheduler or the client machine.
The scheduler basically, it's technically not doing any computation. It's just basically, orchestrate everything. Thanks for the explanation. So let's just start with a bigger array. So this is a 2D array of 10K by 12K, and it's an array of ones. And we can create it. This is first the Numpy syntax, and then we can create it similarly, very similar syntax with Dask. But there is a big difference when you're looking at representation of the data. And you can see that we are not seeing any real value. So for the Numpy array, we are seeing all the ones, but with the Dask array, we don't see any real values. And there is a good reason behind that, and that's what we talked earlier, the lazy valuation. So it doesn't even create the data. Basically is a representation of the data, and when we want our computation to be done, we have to explicitly ask it to. So now looking at the representation of the data, the Dask array, there is this concept of chunks, and this is basically the sub-arrays that basically the pieces of data that will be sent to different workers to do the computations on. And the way that you chunk your arrays, overall chunking is one of the big problematic things with Dask. The way that you chunk your arrays significantly impact your performance, and you should be always aware of the chunking and how your arrays are chunked. You can specify so this was the default chunking that Dask used, but you can also specify it using the chunks argument. And one thing that actually I made that mistake before. So with the chunks argument, it means the chunk shape, not the number of chunks. So if you use chunks is equal to 1, basically that means we have several chunks with one element in each of them. And there are different ways to specify chunks. You can have chunks that are same size. You can have chunks that are different sizes, and there are a lot of different ways to do it. And you should modify your chunks based on your workflow. But let's see how it works. First, the shape was what we have was a 10K by 12K. Now we specified 5,000 by 4,000 chunk shape, so it would be a total of 6 chunks. And each of them is almost 150 megabytes, almost 160. And now let's do a comparison between the Numpy and Dask. So with Numpy, this calculating the mean will take 83 milliseconds. And let's do it with Dask. So now it takes only one millisecond. So you might think, oh, that's very fast, but remember, Dask doesn't do anything until you tell it. So this is just a representation of the data. You have to say, you have to use .compute basically to trigger the computation, and now Dask will basically start crunching the numbers and get you to the real value that you want. And of course, it's not working. I probably, I didn't actually first create the representation. That's why I didn't first run this. That was my problem. So you can see it's much faster than the 81 millisecond that we had with Numpy. It's now down to 19 milliseconds. And what basically the compute does, or the compute method does, is that it converts your Dask array to a Numpy array. So and that's what we want to avoid. So you should think about avoiding using .compute and basically loading your data as much as you can, and put it further down your workflow. So use .compute as less as as you can and try to use it wisely. So for example, first reduce your data size and then use it. So filter the data and then use your compute to basically do the calculations. Here we can see, let's see, here we can also see the task graph of the mean calculations that we did earlier. So you can see first it does the mean on each of the chunks, and then it combine them and aggregate them together. And we can look at the sizes of these arrays on memory. So you can see this block basically prints out the shape and the sizes of these arrays on memory. And you can see that Dask array size is 0. And again, that's because it doesn't hold any real values to it. But Dask, there is a way that you can also see the real values, the actual values with Dask arrays. Now let's actually get to larger data sets. So this is a 3D Numpy array and that we are using now. Basically, first actually, so let's actually look at it in that. So it's almost 6 gigabyte of data. So it's almost too big for basically the machine that I'm running on. So I cannot even create the data set. So that's why I commented it out. But you can see with Dask, actually, I easily created the data. And here I checked the size of the data. You can see the computation. I mean, I even couldn't load the data on with Numpy, but you can see that the computation is relatively fast using Dask. And Dask basically did all this computation. And this is actually a more complicated computation than what we had earlier, which was just calculating the mean. Yeah, so that's what I wanted to cover in this section. A big thing overall, like a take-home message in Dask arrays is that always think about chunk and try to avoid compute as much as possible. We will talk about rechunking a lot more in detail later in the tutorial, and Brian will cover it in details. But I put it together a few examples basically to show you how different chunk sizes impact the performance. So if we have a chunk size that are too small, it will be bad because we are introducing too much overhead. And if we have a chunk size that are too big, it would be bad because we cannot even fit it into memory. So as a rule of thumb, your chunk sizes should be small enough that they can fit in, they should be small enough that they can fit into memory, but large enough that it doesn't add more overhead basically to your computation. Yeah. Go ahead.
Do you have an idea of a ballpark of what's a sweet spot?
Yeah, that's a good question. So the way that actually Dask like the guidelines, it says 100 megabytes to like 1 gigabytes. Nothing more than that. Definitely more than 1 gigabytes is like too big. And if it's like smaller than 50 megabytes, it probably will be too small. So something around 100 to 500 is probably optimal. What do you think?
Yeah, no, that's a general good rule of thumb. And I just wanted to say that we'll show some examples of that in a full notebook in the second half of today's session. So
Definitely, yeah.
hopefully we'll prove that to some degree versus just giving you a rule of thumb.
Yeah. Yeah, so with that, we kind of now are familiar with Dask arrays. We know how Dask arrays work, when to use Dask arrays and whatnot. And yeah, so if you don't have any questions, I can move on to the next collection, which is Dask data frames.
So I think there's two things we could touch on. So Cecile had mentioned in the chat that when you run these cells multiple times, the variability in the execution time can be kind of significant on computations of this scale. And I said this in the chat, but like one big factor for that is the first time you run it, you're going to be allocating data structures, and then after the fact, Python can reuse those, and you're going to have some computational savings. So that can introduce some variability. And there's also, like, for something this short, if your system has, the node you're on or the computer you're on has more load at any particular time, that can, cause things to run a little bit more slowly. Or if you're still using like a hard disk, it could have to spin up. So there's, various things that could go on there. And if you really want to do like benchmarking of that style, you'd probably want to, do multiple iterations, and then kind of get a nice metric that way. But, for this, we're just trying to hopefully demonstrate something and not, take too much time. It's always a balancing act in these tutorials.
A technical question. Can you go back up before you do the Dask compute? You have like yes. So you have this dot mean that you're invoking here. So clearly at this point, like you mentioned, there's no computation being done. So what is happening? You're calling mean, but is it storing a process that's like, if you hit compute, I will do it?
Exactly, that's what it does. It basically creates the task graph for it. So the task graph would get more complicated and more complicated as we go along, as we add to this. But it doesn't do any computation. It just creates the task graph, and when you hit the computer, or also you can do with .load, it then starts saying, okay, so this is the task graph, this is what we should do, and you will send the chunks to like the workers and.
So you could create like a list of action to put in memory, and then you would just execute them.
That's exactly how it works. And that's why I said you should avoid using .compute early on in your computation. So if we were like, say, for example, and here we are even like doing that. So if we select, for example, if get basically like filter the data somehow. And the same is true with data frames as well. If we filter the data, if we like either mean the data or like do some sort of filtering and reducing the data, then computing, it would be better, because then that you don't have to have like basically carry around that large array in your memory. And that's how Dask actually is doing bigger than memory calculations.
Yeah, I guess just to add to that point, the reason that the Dask can enable these like operations on very large data structures is because it only brings in data kind of on demand, unless you tell it not to. So if you run .compute a lot, then you're having to do that data, loading the data on the workers repeatedly, and that's really going to slow down your computational workflow. So trying to only run .compute when you need a result is a general good rule of thumb.
So I've also used .persist. Is that kind of just running in the background?
We'll talk about that.
Okay. Sorry.
But yeah, no, that's fine. And that gets into that whole like telling workers when to keep data around.
Okay.
Exactly. Yeah. That's like kind of, keep it in the cache. But yeah, we'll touch on it.
So another question. When we think about workers, can we draw a parallel with processes?
That's a good question. So,
like if I had like one very old computer that only had one processor, could I still invoke like several workers?
yeah, that's the case. So for example, if you have a 4-core or like dual core computer, you still can have like 20 workers, but would that be an efficient workflow, or would like using something like for example, using threading or like avoiding having like as many workers probably might be better. So it's not similar, like in that term, it's different from like high performance computer, where you can have like basically like your processors are basically very defined. With Dask, you can have as many workers as you want on a local machine, but that wouldn't probably be an efficient workflow, because you're adding a lot of like communication between the workers and yeah. So the worker is like basically think of it as another Python instance, like on your. That's how I kind of think about it.
Yeah, and I mean, in the simplest case, like if you had an old like Pentium 4 or something and it only had a single core, there'd be absolutely no reason to run Dask on there, because probably the overhead of trying to utilize multiple threads, and maybe if you have a very high file I/O workflow. But like Megan was saying, you might just want to use Python multi-threading there and avoid Dask entirely because you're just going to add overhead. But yeah, at the fundamental core, depending on how you configure Dask, you can think of a worker as like almost like an MPI processor, a Python process, like Megan said.
And it's gonna work best when they're homogeneous, they're all equally capable.
Sure, yeah. Okay, we can go to the next tutorial, which will talk about Dask data frames. In this tutorial, again, we're going to get familiar with basic concepts and features of Dask data frames and when to use Dask data frames and how they're different from Pandas data frames and what are the built-in operations that we can do with them and what are Dask data frame best practices. So Pandas is very, very popular for working with tabular dataset. But the data needs to fit into memory. As a rule of thumb, you have to have 5 to 10 times as much RAM as the size of your data. And that's when, again, Dask comes to the rescue. Dask data frames, you can think of them as parallelized version of Pandas data frame. A Dask data frame is basically, technically, is composed of like smaller Pandas data frames. And here, the terminology for it is that they are partitions. They are basically, they have a very similar API. They feel exactly the same and working with them. It doesn't have as extensive as of an API as extensive functionalities as Pandas data frame, but it has the most popular ones. It almost has all of them. And similar to Dask arrays, Dask data frames are also lazy, means they use lazy evaluations. They don't hold the data. They just have this basically representations of what needs to be done for the computation to be completed. There are sometimes there are some very good cases for Dask data frames. There are some workflows that they would be very good for. You can think of them as whenever you have parallelizable computation, usually Dask data frames are great. So if you are doing any element-wise operations, row-wise operations, or things like that, finding maximum, those are great examples. But if you are doing any reshuffling of the data or reindexing of the data, then that's data frames. And that's because the nature of these tasks are not technically parallelizable. So Dask data frames are probably not a good choice in those situations. And I put a warning here that although they have a very similar API, it does not include all the Pandas interface yet, and you should check always beforehand. So in this notebook, we are going to use the tutorial dataset that we are going to use is from NOAA, and it's a real dataset that our scientists use every day at NCAR. So it's basically global historical climatology network data, and it's the daily averages that we are using from NOAA, and they have basically climate records, daily climate records from more than 100,000 stations across the world, and it's a huge data set. I put some references to the paper and also website. So for this tutorial, to get the data, this is a wrapper code basically that get the pre-processed data. But the data set is also available, the real data set, the big data set is also available through the website that I put there. And actually at first I put the whole data in this notebook, but I was thinking that probably that would be problematic. If you run this, it will basically download the data for you and then put it in the correct directory for you. So with that being said, after downloading the data, we can start working and interfacing, basically playing with Pandas data frame to get familiar with Pandas data frame. So first and foremost, I'm reading only one of the files that we've downloaded. It's basically climatology record for Denver International Airport. And we are reading the data using the read CSV, and it has some built-in functionalities to parse the date. And then here, I'm just looking at the top of our basically data frame, and we can do, for example, tail to see like the bottom of the data frame. And I just like put this here so that you get familiar with the sorts of things that we can do, like different computations that are possible to do with pandas. And you can also see like what columns are available, and we have maximum daily temperature, minimum daily temperature, and different flags, and like snowfall, daily snowfall, different variables are available. So I put together some operations that we can do on a pandas data frame. So for example, this one is a slicing, basically a value-based slicing that we can do. So let's actually remove this, the rest of this basically. So if I basically run this, it will only like basically slice this data to find the data only for last December and look at the data for last December. And then if I run it like this, it will basically load the minimum daily temperature for December of last year. And if I add the IDX mean, which means find the index of minimum temperature, so that would find the coldest day basically of December of last year. So again, similarly, we can do plotting with pandas easily with just one line. So here, similarly, I just sliced the data first and then selected the snow depth and then just plotted it. I added a label to this, and easily you can create a plot with pandas data frame. This is a little bit of more complicated situation, complex analysis. So here, first we filter the data to find all the days that have snowfall more than 0. So here we are basically finding how many snow days we had each year and finding like which years we had the most snow days. So we first actually select the days that we have with snow bigger than 0, which has like, we have like some snowfall, and then we group them by year to find basically the snow days per year. And then if I run this, it will return only a group by option, but with group by you can do size or mean or unique, or basically do different, you can do different calculations with it. So here I'm doing, basically I'm just like running size to find the size of each group, and then I am sorting the value using the sort values. And then I changed the order to basically sort them in different order. And then I'm running head to see the first 5 years, and that's how I have the first 5 years. This one is one that I thought it would be fun to do in this tutorial. When I was actually writing this tutorial, I was very cold. That's why all of it is related to cold temperature and snow and everything. So this one was we've heard that this might be first year in 13 years that we didn't have any days with temperature above 60 degrees. And here we did the same. Basically, we fact checked their headline with just one line. Here again, similarly, we did this basically filtering of data. We selected January. And then we basically find the years that we have, like after the years that are greater than 2010. And then we filtered the temperature, the maximum daily temperature to basically for greater than 60 degrees. And actually the units here are a little bit weird. It's a tenth of Celsius. So that's why you see 155. I thought I'm crazy, but no, that's not the case. The units is a little bit weird. And then if I run it, it basically just filters this data. And then I am running now group by to group it by year and then find the size of it, similar to the example above. And then here we can see the number of days above 60 degrees since 2010. And you can see we didn't have any in 2023. So that headline was true. So this is all great, but you might ask, what's the file size? So the file size here is relatively small. And because we only analyze the data for one station. But what if we wanted to analyze the data for more stations? And actually something that we should also check is although the file size is almost 4 megabytes, but let's check the size of the variable on memory. And we are doing this similar to the previous tutorial with the same function. And checking the size of this variable, the data frame on memory, you can see it's almost 33. So it's the same and the same, basically, if you remember, we had that rule that you have to have 5 to 10 times as much RAM as the size of your data set. And you can see it's almost less than 10 times, but yeah, it's almost 10 times. So yeah, that's something to remember, that with even although the file size was small, it needs basically a bigger RAM. Basically, the size on memory would be bigger. And now this is just one station. We have 100,000 stations, more than 100,000 stations, in the world, and we have in Colorado alone we have more than 4,500 stations. So let's scale it up to larger data set, and I just basically run this command, and this is a bash command, to just show what was the total data set that we are reading. So now we are reading almost 600 megabytes of data. And with pandas, you cannot technically read all the files at the same time. So here, if you see, I am basically running a loop. So you can see that I am finding all the file names that are in my path, basically, and then running them in a loop and then concatenate them. So with the concatenate and running them basically using this syntax, you can technically do it in one line. But with the read CSV, technically, you cannot read multiple files at the same time. And here, let's read all these files. And you can see it will take a while to finish.
You can also see your memory going up there on the bottom.
Exactly.
I know people remotely can't see my point, but
Yeah, you
on
can
the
see.
bottom of Megan's screen, there's the memory tracker.
Yeah.
It's done right.
Okay, yeah, almost done. And you can see now we are really pushing it. So here, and what's it?
It's still low. I get it up to like 40, like 80 gigabytes out of 4 gigabytes. I don't know how, but it happened. People getting crashed.
We reserve the right
Yeah,
to
you-
kill you. It's not guaranteed.
Still actually.
I always ask.
Yeah.
One for.
Yeah, if you're following along a situation like that, you see that tracker go above 4 gigabytes, it will, independently of Dask, it will spill the disk. Or actually, it's kind of a high-speed memory, high-speed disk cache used as a memory. So we put that in place so things on Casper won't fail outright unless you go way, way, way above. But your performance will slow quite a bit if you're going above the allocated RAM.
And actually, like for this example, I intentionally got like 4 gigabyte because I wanted to show you that it's still possible to do this calculation using 4 gigabytes. So this is only 66 stations, and if we have even more, then that would be even not possible at all to do with pandas. So here, this is a little bit of more I basically calculated the snow days per year per station, and if I run this, I put it up there. It will take around 90 seconds to finish, basically to show me which Colorado site among the sites actually that we've the selected sites, because at first actually I had like the whole data set, but it was too big. So among the selected sites that we have, which one has the most snow days in 2022 or 2023? What?
So for some reason, the data I downloaded was double the size of yours. It's 1.2 gig.
Yeah, that happened to me too. I'm not sure
Yeah.
why.
So I think if people are only using 4 gig, it'll take a
Then
lot
definitely
longer.
that would be too small. Can you see how many files there are there?
I mean, it says there's 66 sites.
That's good.
Because I have the same issue.
Then, okay.
Wait, I
5 gigs.
I have 67 file. You have
Yeah, it should be-
67.
Yeah,
Sorry?
it should be, I intentionally, like, I did it last night that I actually reduced it to 70, like under 70 sites, so it would be smaller, but it seems like it's still, too big. So if it's too big, I'm sorry, yeah, you should use a bigger RAM tool. I mean, you don't have to like run it through the pandas part. This was just a demonstration. We can do it with Dask, you can see it will fit into, you can still use Dask basically. So here, this one finished in 1 minute and 21 seconds, and here actually I delete the data frame, the pandas data frame that we create first, just as a cleanup. Now let's actually do the same thing with Dask data frame. So
Yeah, Negi made a point, just so everybody online. If you went over memory in the pandas part, don't worry about it. We can work those, the demonstration desk will be fine later on.
yeah, I'm sorry about that. If the the data is too big, I thought it should be definitely smaller than that. So now start with Dask data frame, and here again we start with again similar to the last example. Here we start with the local cluster and our client to have our work areas, and this is actually nice because it gives us also a dashboard that we can see. We can track different diagnostics on it, but I'm not going to go over this now because we're going to cover it in the later tutorials. What are the widgets that are available here? And now first I create this cluster, and then now let's try to read all these files using Dask. And using Dask, actually one nice thing about it is that you remember, if you remember, I mentioned that with pandas you cannot read multiple files at the same time, but with Dask this is possible. So I'm reading all these files at the same time. With pandas I had to do the concatenation. And here it reads it pretty fast, but you can see in the and DDF here, I'm basically putting everything in DDF, and that means Dask based. That's like a common variable name that is used using Dask. But anyhow, so you can see when I am like looking at the representation of DDF, it's basically empty. And I actually did like, for example, like select the Tmax or did the mean, and you can see it's still not showing any real values. And again, that's because of the topic and that we talked earlier, the lazy evaluation. So this basically this is just empty. This is basically hold some information on how to generate the data. It doesn't hold real information, the real data basically. It's just a task graph. And you might ask, when I'm looking at my data, I can see the columns, or I can see the type of each column, and how can Dask know that without reading the data? And that's because actually Dask reads the first file and then basically assumes all the files are using the same format and basically enforce that and think that all the files are similar, while that might not be true. And that's actually a point that can be like problematic using real data sets. So again, this is a pre-processed data. But if you're to use real data, you might read your data set and it will work fine. But then when you hit the compute, when you want to do the real calculations, you see that now you'll get some errors on reading your basically CSV files. And that's because, for example, some column is missing, or some data type is not matching. And to avoid that, actually, it's best to always give Dask the type of the basically each column. So give a list of like types of each column. But here, because we were using pre-processed data, it was cleaned out, so we didn't have that problem. And we can do we can use head, and similarly, we can use tail, similar to pandas, and see the top of our data. So when I hit head, actually, you can see it now. It actually generated that it went and basically read my CSV files. And that's a nice thing. So it doesn't fill up the RAM that way. It basically just holds the task graph, and that's how it works on the bigger files. So here, let me do the same calculation that took almost 90 seconds using Dask, and you can see this one should finish relatively fast. Yeah, 4 seconds. So you can see how faster this is, and that's major improvement from 90 seconds to 4 seconds. You might think nice, but what went behind the scene? So here I showed this is again a high-level graph. I showed this high-level graph of what was happening, what were the steps that Dask did. And you can see Dask basically the first step was basically reading the data and then selecting the columns that it wants, and then selecting, for example, the greater than, and doing the group by, and then finally aggregations. So you can also like see the low-level visualization, but I think it might be best not to look at it because it's just so big that it might not make sense. But and there are some engines that visualize that Dask has that make it interactive, so you can like zoom in and out of the low-level visualization, and those are useful. But I didn't want to add another basically dependency here. So let's actually. Another thing that is definitely a common theme that here we have is that using compute wisely. So I put together a few examples of using compute differently and seeing like how much it impacts the performance. So one big thing is that when we use compute overall, like when with Dask, we can now share the intermediate results, and that's actually very beneficial in some cases because technically now Dask doesn't have to do some computations twice. It just only do it once and then share the intermediate results. So in this example, I am basically selecting the snow days, and then I'm getting the minimum the average maximum daily temperature and standard deviation of a maximum daily temperature. And now if I hit the compute on these two, it will take approximately, hopefully 10 seconds to finish. 7 seconds to finish. And now let's do it only once, and so that they can share the intermediate results. And you can see it should take almost half as long. Yeah, it took almost 4 seconds. So it's much faster. So that's why we think that using the compute, thinking about all these pieces and where you want to basically, where you need the computations, it's very beneficial. And also you can see if I basically look at the high-level graph, you can see that we are like first reading the CSV and then selecting the data, grouping the data, and then doing the sum, aggregations, things like that. So it's just useful to look at the high-level graphs and low-level graphs to see what are the computations that are happening.
Yeah, and I think the important thing to note in that high-level graph there is that only some of the steps get repeated. And that's where you're doing this, that's where you're getting the savings from running those compute operations at the same time.
Exactly. So doing like basically, yeah, some of the steps are very similar. And that's how basically they are sharing the intermediate results. So when you're doing it only once, then it would be much more beneficial, as Brian mentioned. So another thing that we can use with Dask, another method that we can use with Dask is the persist, which basically caches the data and keep the intermediate results in memory. So it would now be different from the lazy, basically the concept of lazy evaluation that we said. Now we are actually putting everything on memory. And the persist would be useful, but it should be used very carefully. So basically what persist does is that put the data now on RAM. But it's beneficial sometimes because we do not want to like put large data on RAM. So we want to put like we want to load when we kind of like slice the data, when we reduce the data. Now that's when we want to basically use persist to basically keep the results on RAM. So for example, here, I do not load all the data. As you can see, like when I was trying to use Pandas data frame, when I was using Pandas data frame, I couldn't like load load all the data. So here I'm just like selecting, for example, Boulder, like from all the stations, I'm just selecting Boulder, and also I'm selecting the days that we had snow. And so I reduced the data, filtered the data, and now I'm calculating the mean, the average of maximum and minimum daily temperature, and printing them out. And now in the next example, I'm using persist. So when it's smaller, when the data is smaller, because here I just filtered out a bunch of columns and a bunch of like basically rows, the data is smaller. And now when I loaded it into RAM, it's much faster. So you can see that now it's much faster. And the reason is that it doesn't require it to go and read it from CSV and do like a lot of things from the beginning. So you should use persist, but you should use it very wisely. And Brian will also cover a lot of good use cases of persist. I just wanted them to be familiar with the concept.
Yeah, and I think, you know, the important point with using it wisely is obviously when you persist something into memory, you're going to use up a decent portion of your worker's memory. So it's going to stay there basically until you de-persist it. For a data set of a large size, you would never be able to persist the raw data into worker memory because you're just not going to have enough space. So it's still like a situation where you would want to do reductions like Megan said. And then once you have a size that you can fit in there and then repeat operations or do additional operations to save time, that's when that workflow would make sense. But it's generally something that you're not going to be able to do with the raw data unless you just have a tremendous number of workers with large amounts of memory.
Yeah, it would be counterintuitive because like the whole point with Dask is that we can basically not hold the data all on RAM. So basically we have data on disk and then we read it whenever we want it. But with persist, we load it on RAM, but it should be used whenever the data size is small enough that we can basically load it.
Yeah, especially if you have a situation where you have like way more chunks than the number of workers, because then you're going, like if I had 8 chunks and 4 workers, then if I persist data from those chunks, it's basically going to be like 2x the storage requirements on each worker.
So I've looked back at my stuff and it looks like I generally use it when I'm rechunking. I don't know. This is all based on learning from other people's things. So this is why I'm here, because I don't know what I'm doing.
Well, that actually sounds like a good practice
Okay.
to me, because, and we'll talk about this more later, but rechunking is a very expensive operation. So generally after you've rechunked, you'd want to save the rechunked results. And you could either persist that in worker memory and use those in your notebook moving forward, or you could even save them to a new file and then bring them in if you were going to rerun that script or notebook a lot of times. So that sounds like a good use case for persist to me.
Go ahead, Phil.
I just want to say that maybe it's because I don't have enough memory, but the notebook are not running. I don't know if other people have problem, but I have this
I will
memory
take a-
usage.
Yeah, I will take a look at it during the break. So we're gonna have, when I finish this, I will have,
Okay.
gonna have like a 5-minute
Okay.
break. And then after that, we're gonna have like a longer break.
Okay.
Yeah, sorry, if we didn't have the room hot mic'd, I would. But thanks for letting us know.
Yeah, just to know that.
Okay, so in general, like I put some Dask data frames best practices in this notebook, and you can read it at your own time. But overall, it's good to avoid, for example, things like reindexing, reshuffling. Those are usually not good with Dask data frames. And reducing the data as much as possible and then loading it onto memory. That's always important. Checking partition sizes, that's another important thing. And you can change the partition sizes using the block size argument. So that's something that I put in there. And then, and then smart use of compute that you mentioned earlier. And always shut down your client so that you don't have idle workers, for example, if you're running an HPC system going wrong. So yeah, let's take a 5-minute break and then we're gonna get back with Dask XR. Okay.
And if folks online have any questions during that break, just put them in the chat and we can answer them out of band.
You have an array and you're chunking it.
Yeah.
Like in the first example, show the 2x2 shape for the is Dask doing the optimization of the size of the array that you're disposing of?
So when you
so right now, for example, here she had like a 6,000 by 4,000, so they're each 3,000 by 2,000. It works well.
I see.
But like if they were both, prime numbers, they don't divide evenly. But
Yeah,
that's still
So that's something
here.
it's like scroll in the array notebook, right?
Yeah.
Let me find the examples.
But even this one is, it just works out to be like 4 by 4.
Yeah, so here it's actually, even though it says chunks, it's not actually the number, it's the size. So there she's explicitly asking for 2 by 2 chunks. If let's say it was like a 5 by 5 and you asked for a 2 by 2, you're gonna have remainder chunks on the sides that are not, optimally sized, I guess. So it does.
So
Thinking about that.
so I see.
I'm not sure if that gets at your question, but
So this means if you had a 5 by 5, then you would do 2 by 2s, and then there's going to be like the leftovers wouldn't be part of the computation.
well, they will be part of the computation, but you're going to actually, instead of having 4 chunks, you would end up having, you'd have 9, and then those remainder, because it would be basically like it's going to divide. You'll have 2, 2, 1 on each side, right? So essentially, you're going to have a 3 by 3 collection of chunks. Since you have those remainder, and those last chunks are just going to be smaller. They're going to be half the size. So it'll have to operate on those later chunks, and like it'll do them in sequence.
They
basically.
will comment
Depending on how
go
many
to the
workers you have.
detail.
Let's say you had
The task. It
4.
was in this.
Let's say you.
Number
Okay, so if you have a
one
2 by 2, you have 4 workers.
Just we run this
Here.
Yeah. Oh, you just run it.
Yeah.
But well, where do you?
I think you need to clone the.
Oh, I didn't clone. Yeah, okay. Oh, yeah. Yeah, I didn't know.
Okay.
2 by 2.
All that, yeah.
So that's
I'm choosing it because I'm looking
here.
up
but then,
Cheyenne and she's saying.
Oh, you're on Cheyenne, yeah, not Casper.
Yeah, it's yeah. So if you can, obviously you want
But
to
I'm
say
afraid
that
to
the
look out.
kind of evenly divide.
I don't know if I can come back.
Yeah.
Real practice is where you can.
Yeah, but can I'm ready.
I think we'll see that in some
I
of
asked
the
her.
graphic representations. Some of the more complicated examples, probably in the X-ray
Got
section.
lots of money to your.
No, not that.
Thanks for the question.
It always
That's
looks very, very minimal, and I haven't been yelled at.
Okay.
Good. I'll just put it that way.
Yeah, where was that clone address to?
Compared to, like,
I didn't pick up this connection, but
Yeah,
I think
okay.
it's going to be up this page
Maybe I'm
here.
going to add a server.
Oh, I wasn't yet.
Yeah, put the NCAR. By NCAR.
Stop this
I lost my connection.
one.
But if you type NCAR in the Dask tutorial,
Then
you'll be able to see the files.
Then you have this session, it's for beginner, and then you have more intermediate after.
Yes, yeah, so
Just
after
to,
I'll cover Dask and XRA, which would be still in the beginner. Then we're gonna go on Dask and HPC, which would be more on like running Dask. Basically, so far what I'm doing is that I'm using technically a local cluster, just basically one machine, basically.
Mhm.
Think of it as just.
Yeah.
And then when the data gets really big, actually, you need to run it on multiple machines. So that's actually when we'll interface basically with PBS, and then Brian will cover that.
Okay.
So we'll submit the job, for example, to Casper, and then
Yeah, because I might stay for this one and try to assimilate this and that. But everything is recorded, or it's available anyway.
yeah, definitely that. Everything is recorded, and yeah.
Yeah, you want to see my error? I'm going to try to go in Casper. She thinks it might be because I'm on Cheyenne and not Casper, but this is what I'm getting.
Multiple times on Casper, and
Yeah, that actually would make a lot of sense because we don't have that disk buffer on Cheyenne.
Okay, yeah.
So yeah, I would, that's a
And I
good
get
point.
already because I was, I get already my session, and I used the same that I was using this morning, but it was on Cheyenne. And I'm going to get out and
get on Casper. Yeah,
and see if it helps.
That'd be a good thing we can mention to everybody.
Yeah, because I will, each time I will get this error and she will not.
That's frustrating.
If CC.
It is frustrating.
Yeah, so for those who are remote, yeah,
Are you
we
managing?
discovered in this room that if you try to run these
I don't have.
notebooks on a Cheyenne session, you're probably going to run into some memory limitations.
On the guest.
So running them on Casper is the intended place to go. So we should have said that more clearly at the outset, but
yeah, that's right.
thanks, Cecile.
Yeah.
Okay, I think we can reconvene. Do we want to, I think Ben is not here.
Might have had to run to a meeting,
Okay,
actually.
okay, so then I'll start.
But we do have one question. real quick.
Okay, go ahead.
So in the chat, when I was trying to see the dashboard, I couldn't load it due to a bokeh issue. Have you had this issue? FYI, I'm currently running Dask from my local machine though.
So that might be, so you have to have bokeh installed for those basically widgets to work, and you have to have, I think it's Jupyter Lab widgets also that you have to have it installed. If you don't, then the widgets won't work if you are using the widgets and dashboard. Yeah, the dashboards all are in bokeh, so that's another.
Yeah, I mean,
Maybe that's the case. Okay, you have it installed, then I'm not sure.
yeah, it's tricky to debug from a local machine. I will say from personal experience, I think it's a lot easier to spin up the dashboard and run it when you're running an organization's Jupyter Hub because you don't have to deal with like potential tunnel problems. You don't have to deal with version problems and all of that. Yeah, I guess unfortunately without looking at the exact error, it's hard to know exactly what's going on there.
So, okay, thanks, Brian. So yeah, let's start with the third part, which is basically parallelizing X-ray with Dask and X-ray and Dask together. So overall, a lot of our users are using X-ray. It's very popular at NCAR, and I'm not going to cover background on X-ray, similar to how we covered background on pandas. But just know that we can, with X-ray, we can have Dask back objects instead of NumPy back objects. And in this tutorial, I'm going to show you like how they relate to each other, and also how you can extract Dask arrays from an X-array, and also how you can do built-in operations with X-array data arrays. Yeah, a lot of users are familiar with X-array. It's great. It's basically awesome for reading netcdf file. And I'm not going to go into details about the X-array. Just know that it's very good for reading in labeled multidimensional. So that's the keyword that you have to remember. It's great for reading multidimensional or n-dimensional. And with pandas, we have only basically 2 dimensions, but here we have like with our data set, basically, for example, climate data set, we have basically multiple dimensions. So for example, this image kind of show it. We have like the latitude, longitude, we have the time dimension. And this one, for example, that we are showing, this is an example kind of like showing the netcdf file, for example, that has like a temperature and precipitation. It has latitude and longitude. And then, yeah, it has the variables, it has the dimensions, and it has the coordinates. So yeah, just to get familiar with the whole concept. So X-array has 2 basic data structure, data arrays and data sets. So data array basically hold a single multidimensional variable. So one of these, for example, it basically holds one of these besides the coordinates and the dimensions and everything. And the data set holds multiple data arrays. So it holds multiple, so think of it as holding multiple variables or holding multiple data arrays, basically. So it holds like all these, and also it again holds the coordinates and the dimensions and all the metadata and everything. Yeah, some basically essential wording to get familiar with as like dimensions, the coordinates, the attributes with data arrays. And I'm not going to go over these again because a lot of people are already familiar with this. But X-array has a limitation, and that's when data doesn't fit into memory. And that's, again, when we use Dask. But to get familiar with Dask data arrays, I put together this example, which kind of shows how it relates to NumPy arrays and Dask arrays. So here in this example, I start with basically creating first a simple NumPy array. It's just a random number. It's a 300 by 450. And it can be like any value. Think of it here, for example, I wanted it to be sea surface temperature, for example. And then I convert, I'm not sure why this isn't running, but then maybe to restart again. Maybe that helps. Second.
I'm having network problems. So.
I have no internet anymore.
Oh,
Yeah. Oh, okay. It's not
Nice.
fantastic.
I still have, no. Yeah, I still have.
And now that one is connected too. Okay. Sorry everyone for the technical difficulties. Yeah.
Ben, since you're connected, can you see now?
Yes, I can.
Okay, excellent.
So what we did here basically is that we create a NumPy array, and I just actually basically printed out the type to make sure it's a NumPy array, and it's a NumPy array. So then we converted it to Dask array. So we talked about Dask array and NumPy array, how they relate to each other. This is great, but let's see, what if we want to have basically coordinates attached to this? And what if we want to have dimensions attached to this? And that's when data arrays are very useful. So here, I converted this Dask array to data array. So basically, Dask array can have data arrays underneath them, so they can be like a wrapper around data arrays. But the data array without any dimensions and coordinates isn't much use for us. We want it to have basically the reason that we are using data array. That's X-array data array is that. So here I added some dimensions to it, and then I created some values, just random values, and attached it as latitude and longitude, and then I attached some attributes to it, some descriptions, some units and things like that. And with this example, I just wanted to show you basically the takeaway message is that X-array data array provides a wrapper around arrays, and especially around both Numpy arrays and Dask arrays. And that actually what makes the X-array data arrays and X-array overall very powerful. Because now we have the capability. Now we have the capability to now we have the capability to use it for large data sets. Now we have the capability to use the same benefits of Dask array. So now let's start with our example here. So here first, again, I started with a local cluster and I connect the client to it. And now I'm reading multiple files. So again, with X-array, I'm not going to details about like opening files and things like that. So X-array has this function called open multiple file dataset. It has the open dataset, which is used for one file, and then open multiple file dataset. And here for this, I'm using the CSM large ensemble datasets, but I'm only loading one of the ensembles, and I'm loading the 2-meter temperature for this analysis. And here, first, I'm finding all the files that are in this directory, and then I am using XR open multiple file dataset. And you can see basically what it does. It's that it reads all the files, it concatenates them using the ensemble memory basically dimension. It combines them, and when you use parallel, that's when it basically use Dask underneath, and it it basically parallelize reading the files. And we can give it different engines. So for example, it has ZAR engine. You can use it with ZAR files. You can use it with NetCDF, but this example is a NetCDF. So here we read in the data, and you can see when we are looking again at the representation of our data set, there isn't any, again, values attached to it. We can see the coordinates, dimensions, the variables, but there are no data. And again, that's because we have, in X-array, we have data arrays underneath, basically. And data arrays, as we mentioned, are using lazy evaluation. They don't hold any values. And again, I just, like, for example, selected a variable and did the same thing. And again, looking at the representation, you don't see the data. One, again, important thing similar to data arrays, one important thing with X-array data arrays, similar to Dask data arrays, is that look at the chunking always and see how you are chunking the data. And basically in the Dask array example, you see how chunking impact the performance. And here it's the same thing. Chunking will impact the performance. And you can specify the chunks basically using the chunks argument. And here, for example, I'm giving it the shape of my chunk, and I'm just giving it in 2 dimensions. So in the other dimension, I'm not giving it in the other dimension. So you can do different, again, chunking. And here, using the chunks argument, now I created, because it didn't run this. We created the same thing, but with different chunking, basically. And You can check also the chunk sizes using dot chunks and the chunks parameter basically. And that's usually useful to look at. I'm sure Brian will cover this a lot more in depth, but that's what I wanted to kind of cover here to get you familiarized with the concept of chunks in terms of X-array dataset, X-array data arrays. And so so that one might be due to like lacking one library. And so are you using the MPL 2023A? So one of our users had the question that they have problems. Are you using Casper?
Yeah. I'm logged into Casper and I was just running through your notebook as is.
Interesting.
Hadn't edited anything.
Does anyone else have this similar problem? It's basically the CF time issue. But there are ways basically, and actually that error happens when it's missing the library, but there are ways actually to convert that data, basically the time. I'll discuss this basically maybe later, like after the tutorial, I can explain that better. But basically you can add with open dataset and with open multiple file dataset, you can also add a preprocessor to it, which basically convert, for example, your time objects to another time object or do different things. But I think that's due to missing library, but maybe I'm not sure what if you're using MPL 2023, why.
Yeah, I mean, that's a tricky one to kind of diagnose on the fly because despite the fact that like using a Conda environment should isolate everything and should ensure reproducibility, you still kind of outside effects from like user settings, maybe Python packages that are installed in a user space. So I think we'd have to take a pretty close look at that to figure out exactly what, but if, of course I don't have my laptop right now, but I think longer term, if we want to solve that problem, you could send an email to either of us or send in a CISL help ticket. We can certainly try to take a look.
Yeah, for sure. So yeah, thanks, Ben. So yeah, you can see that yeah, using chunks, you can check the chunk size, and again, I mentioned like Brian will go into more details about chunks. That's one of the big things that impact the performance of Dask. You can similarly use Dask Visualize to basically check the task graph of Dask arrays. And here, for example, I'm using Dask Visualize to check that this is the mean, and yeah, you can check it. And again, as I mentioned earlier, these might get like really confusing, but these are usually like good to check to see if there are areas that can be optimized or can be basically like, for example, if your chunks are not like they're odd numbers, they can like, or they are like, they made the graph looks not optimized, then you can basically tweak things around it. So this is a good thing to always look at. And similar, so if we want to get to the real values of this to our variable, similar to Dask arrays, we need to use either compute or we need to use load. .load. So there is a difference between .compute and .load. It's a very tiny difference. And so far we only use .compute. So .compute basically what it does is return an object, basically similar to whatever you have. For example, if you have an X array, it will return the object similar to that X array, but with numpys underneath. You remember the compute converted to NumPy. So it will return the same thing, but with NumPy. So it will return another object. But with load, what it does is that it will basically do the calculations in place. So we'll change it in place and we'll basically, that's how they are, the compute and load are different. So it's a small difference. And then their third option is always using persist. But again, as we mentioned earlier, and we will mention this again, persist should be used very cautiously, like because you don't want to have large similar to compute and load, but it should be used very cautiously because you want to be aware of how much data basically you're loading into memory. So you can, and I mentioned about also, so you can get to the Dask arrays underneath your X-array data arrays using .data. So this will basically return to you, and the representation is exactly similar to how we have it for Dask array. So now when we think about X-array, then you don't have to think about it as something different from Dask data arrays or Dask arrays. So here, for getting the values, similar to how we have it for Dask arrays, we have to do the compute. And another option is using to Numpy, which again, the compute will convert everything to Numpy, and to Numpy also convert everything to Numpy. And there is a small difference between the two of them, but I'm not going to cover that one for the tutorial. So the same basically methods, X-array built-in methods that were available with X-array are now available with X-array that are using Dask arrays. You can do like min, max, everything, group by, everything. So here I'm doing as an example, a single point calculation, and you can see here I'm loading the data. So here I selected the point for Boulder from our huge data set, and I'm loading it because now it's smaller. I'm only basically loading 1 point. And then with the resampling, I'm basically taking the annual average with resampling and doing the mean. So I'm taking here the annual average, and then we can see like if we can, I can plot it. I cannot plot it. It seems like. Yeah, this one. Is this the error that you were getting?
Yep. Well,
Okay, but the thing that I wanted to mention here with the plotting, it is not important. So don't let's not get worried about this error. So what's important here is that with dot plot, also be always careful. It's similar to compute. It will load the data. So that's what I wanted to mention here. It would just show an ugly plot. But always be careful with dot plot too, because a lot of people want to like see the data, but that's basically also loading all the data into memory. So, and it will, if your data is big, actually it will take a long time to do the plotting. So now let's do bigger calculations. So this is, for example, converting the units, and you can see now it's actually, again, not taking that long, or it shouldn't take that long. But if you want to do a little bit more complex basically analysis, it will take long with if our X-array is using NumPy array underneath. So here, for example, I'm calculating the monthly anomaly, and if I was using NumPy arrays with my X-array, it will take a long time. But actually using X-array with Dask arrays, it's not taking, it's done much faster. So let's see. Yeah, and you, again, here I'm also checking the type of the data basically after loading it, and also I'm selecting 1 point and plotting it. I'm not running actually the cells now, because I'm afraid that I will get a similar error. But yeah, you can do different things now with your data, but just be aware that first do reduction always. If you want to have like a takeaway message, first do the reduction, first do your basically first reduce your total size of the data set, and then try like plotting it or doing your computations now. And Brian will talk about chunking much more in detail later this afternoon. But again, similar to the Dask arrays, you can do different chunkings with X-array and data arrays and data sets. and it would be different. So the rule of thumb that I mentioned, the Dask and your chunks should be small enough to fit into memory, but large enough to not incur much overhead. Is true. There are more advanced workflows that also you can do using Xarray. So one and Dask, and one is like apply on vectors function, apply ufunc, and that can basically automate embarrassingly parallel functions. So here I did the calculations for saturation vapor pressure, and this one actually it can get like an Numpy array, or it can get anything and return anything else. I return basically Numpy array, or you can get like a Dask array and return Dask array. But the important thing is that it's doing some basically computation on my the input and calculate the saturation vapor pressure. So one way to do it is basically using the Xarray apply ufunc, and that's for when you have a function that isn't basically wrapped by Xarray. So that this function basically has, like, for example, gets Numpy as input and returns Numpy as output, but we can apply using apply on factorized function. One of the applications of it is that we can also use it with now Xarray database. I hope I explained.
Maybe you could mention for folks, like, what would be an example of a function that is wrapped?
So for example, a function like, so something like sum, for example, this is the simplest example, or mean, or standard deviation. Those are wrapped functions. Those are already applied within, those are built-in basically methods inside our Xarray data array or data sets. But this one, for example, we had it, and this works for with basically an array. But here, I didn't care that it works with, like, what's the input and what's the output. I just used it with a Dask array or an Xarray data array. Sorry, there are so many arrays. So yeah, that's just the gist of it, is that you can apply the functions that you previously written for example, doing your computations, for example, doing different computations. You can apply similar functions to your Xarray data arrays using apply on vectorized function. That's the takeaway message from this section. Yeah, that's why I put it in the supplementary material. Overall, good practices is that always check your chunk sizes, make sure they are around 100 megabytes to 1 gigabyte, never over 1 gigabytes, because that's when it will get really slow, and even if it works, if it doesn't crash, it will get really slow and it's not optimal. Always first do some indexing, do some selecting of data, do some filtering, and then do the computations. And when possible, use Xarray, apply ufunc, or apply on vectorized function. And yeah, that's it. That's the summary of using Xarray when that can be basically using Dask arrays. So just the summary, Xarray can use either Dask array or Numpy arrays underneath. And using Xarray with Dask arrays is also possible. That's the summary. I hope I'm not confused. I am not making this more confusing by using so many arrays. So the next, and I'm just going through these fast because we are a little bit out of time.
I think maybe just I'll make a point there, though, that, obviously there's a lot to cover with these various high-level collections, but I think the take-home message is that a lot of the same concepts apply across the board. So, like, you have this concept of, like, a data structure, whether it's a data frame or a data array or an Xarray, that's like has Dask, as the underlying object. Either way, you chunk it up and you send those to workers, and it operates the same. So conceptually, you don't have to think of these too much as different things entirely. It's the same process. It's just you're using that on different types of objects. And then there's also, like, Megan didn't talk about it, and probably most people in our community wouldn't use it, but there's also like a Dask bag, which it's like the Dask parallel version of like a Python list. So fundamentally, they've created this, that if you use a high-level collection, you can have the same conceptual ideas in terms of even like the chunk size guidance, but you're going to apply it across the board, with some nuance for each of the particular types, but.
Thanks, Brian, for that. Yeah, that's what I overall wanted the take-home message to be, just that this wasn't an XRA tutorial. We wanted to just let people know that similarly, XRA can use Dask arrays as well, and it would basically the same rules apply to it. That's the underlying point. So.
Wireless issues in the other building too.
It's an in-person.
It seems like it's.
I think there's something with the Jupyter Hub or
I can't get into Casper.
like everything
Ooh.
kind of down.
Oh, crap.
Sorry.
We can't all touch the wireless router at the same time. That was my fix for your web. You can't do it in the Jupyter Hub?
I can't even get in. I'm in this.
All my other internets was
The terminal.
You're both on the internal.
I'm on visitor.
Me too.
I am on internal.
Like
Got you back on visitor, but I had to come back to the back of the room.
I'm logged in
Thanks.
to Casper on the terminal, and this was from before. It's still on there and still working, but. Yeah.
Well, just what I say to both the remote people and the people in the room, but thanks for bearing with us.
Yeah.
I log into Casper.
Oh, that's unfortunate.
I suspect it's a connectivity issue in the room for us, but hopefully there's not something broader going on. I think Ben's taking a look.
But yeah, but I'm on. I can log into like the Zoom meeting and check my email and all that. But it's just that I can't get onto Casper
Okay.
I can check.
from the terminal.
No, you cannot even check your email. Yeah, I think maybe there is like connectivity issues in this room. Yeah.
Because I was having the opposite problem earlier where I couldn't check my email, but I could get on Jupyter Hub. So it feels like a network thing and not a Jupyter Hub thing, but.
Yeah, sorry for the technical difficulties. Basically this last section, we're going to talk a little bit more about the second component of Dask that we talked earlier, and that's Dask dynamic scheduling, or the schedulers in general. And Dask has several different schedulers that can be used for different purposes and on different machines. But we're going to cover that a little bit here. Overall, for this tutorial, we were meant it to be more on HPC machines. So Brian will cover that part, but hopefully if it works. So we talked about components of a Dask cluster. So the Dask cluster has basically one scheduler. It has a client, and it has multiple workers that are doing our work on the subset of data. And we explained this in the first part, but think of a client as an entry point to talk to our scheduler as the orchestrator between our workers, and our workers are basically the Python interpreters, or like Python processors that are going on. We have technically two types of schedulers based on Dask terminology. So the two types of scheduler, one is single machine scheduler, and the other one is distributed scheduler. So the single machine scheduler manages the execution of all tasks on one machine. And this is actually the default. So when you don't use the client or when you don't use the local cluster, it will use the single scheduler. And it's basically mostly used in situations where we have large amount of data, but it's not that big. So it still can be processed on a single machine. You don't need to have access to a cluster to basically run your code. And this is the default choice by Dask. If you don't set a local cluster or set a cluster, basically it will use the single machine scheduler. And there are multiple different single machine scheduler. One there are, and I actually removed a few of them that were already in there. The ones that you need to be familiar with, or you might want to be familiar with, is single-threaded scheduler. So the single-threaded scheduler, you should be very cautious about it, but it's great for debugging your code and profiling your code. So it will basically turn your code into running and just serially. So when you are like basically converting everything from Numpy or pandas or whatever, and start using Dask, if you have any problems, this can be used as a tool for debugging, besides the dashboard and all the other tools. And then there is the threaded scheduler. The threaded scheduler is basically backed by pool of threads, and it will basically run the task concurrently. But still, they are all in a single machine. And with the compute, you can give it the scheduler. You can say just do like a single threaded. So this way, you can basically debug a small part of the code. And yeah, check that. So check that computation to make sure everything is going smooth. And also you can change the config basically to use a specific type of scheduler. So I put the syntax here, but you might you probably don't want to do this at all. And the threaded scheduler that Dask is using by default is actually the best option. Most of the time.
If you're running a single machine.
Yeah, if you're running on a single machine. And these are all single machine schedulers. But most of the time, so now that's what Dask says, is that most of the time, like 99%, 95% of time, you don't actually want to use these single machine schedulers. You want to use the distributed schedulers. And this is the confusing thing about distributed scheduler, that you can run distributed scheduler on one machine. So you don't have to like run with single machine schedulers. You can run with distributed schedulers. And distributed schedulers, you have to, if you want to run it on a single machine, you have to define a local cluster. And this is what we did in earlier tutorial. So the benefit of distributed scheduler, for example, the distributed scheduler is that it, for example, provides a dashboard for you. You can do like all sorts of diagnostics. You can check the data. And yeah, due to the time issues, I'm not going to go through like all different things. But here in an example, I just compared the performance of different schedulers for doing some computations. First, I'm comparing the single machine schedulers, and then I'm using the distributed scheduler basically. And distributed scheduler, again, you can use it on single machine, or you can use it on multiple machines, for example, on your HPC system. And on single machine, it's basically called local cluster, and you define a local cluster, and you can change the number of workers, you can change the number of threads. And on an HPC machine or on several different machines, and actually there are several different ways to run distributed on several different machines. You can run it on cloud, you can run it via SSH and use like multiple machines via SSH. But you can basically use distributed on either single machine and multiple machines. And yeah, that's the take-home message from this one. And you can also check the dashboard, for example, that it will provide. It's this is one of the winning points for using basically local cluster and also distributed, which is one of the local clusters. So for checking the dashboard, basically and the Jupyter Lab widgets, you can either copy the link basically in the here in the basically. Let me actually try this. You can either click on this, which needs authorization. So yeah, the thing to know that is that you can open the dashboard using the link that's provided there, or you can also copy paste the address, and here on the side you can paste the basically address here, and it will provide a bunch of different dashboards that are available for you. And you can check, for example, how your tasks are progressing, what's the memory usage on each of your workers, and what's the CPU usage of each of your workers. There are, I put in a a bit more information in there about like checking, for example, the dashboard. Also, you can check the local cluster. If you do a local cluster, basically just typing local cluster, it will show you the spec basically of the local cluster that you're running. And yeah, always know that you should always, it's best practice to shut down your client after you're done with your work. And with Dask distributed, again, as I mentioned earlier, you can run it on cloud, on several different machines, or on a cluster. And on cluster for NCAR, especially, we can use Dask job queue, and also we have the PBS cluster. All of this Brian is going to cover at 3:30. But for now, we are taking a break to see if we can figure out what's going on with the connectivity and the connection issues that we are having.
Good call.
Sorry about that.